Hi Year 12. Today's video is having a look at exercise 6B, differentiating trig functions in our Year 12 topic. Okay, so the first thing in your little booklet, I've got a couple of bits of information in there. Yours looks slightly different, so what I want you to do is to copy down what's in here, either the stuff on the left or the stuff on the right. Majority of this, or actually all of these rules are on your HSC formula sheet, and I'll show you that in a moment. But when we're differentiating sine of a function, we differentiate the function, pop the value out the front, and we end up with cos of that function. When we differentiate cos of a function, we again differentiate that function. In this case it would be a, pop that out the front, and instead of getting cos, when we differentiate, we end up with minus sine of that function. And when we differentiate tan of a function, again, like the others, differentiate that function, we'll end up with a in this case, pop that out the front, and we get sec squared of that function. It's written like this on your HSC formula sheet. So where I've got my function here on the left written as ax plus b, your formula sheet just pops it as f, and when we differentiate f of x, we get f dash of x. So I'll pop over to the formula sheet and show you what that looks like. Okay, so on the third page of your HSC formula sheet, this is what you're given, which is exactly what we've just talked about in our notes. So when we have a function that's y is equal to sine of f of x, to get our dy dx, we differentiate this function after our sine to get our derivative of that, and the sine f of x becomes cos of f of x. Likewise, when we have cos of f of x, differentiate the f of x, pop that out the front, and we end up with minus sine of x. And when we've got tan of f of x, differentiate f of x, and we end up with sec squared f of x. So I need you to keep looking at that as we're practicing our work, and always referring back to your HSC formula sheet, because you're not going to get points in the HSC for copying that down, because you've got that given to you. Okay, so we're going to use those rules now, and the first example that we've got here is to differentiate and find the value at pi on 4. You need to differentiate first, and once you've done that, that's when we find our value at pi on 4. So our first question is, why is sine x plus cos x? You're going to use your HSC formula sheet. We're going to differentiate the sine x, and then we're going to differentiate the cos x. So dy dx, or y dash, becomes, when we differentiate sine, we get cos. When we differentiate cos, we get minus sine x. So that's our answer. I haven't had to pop a derivative out the front, because when we differentiate the x behind the sine, we end up with 1. So I've basically popped a 1 out the front. So this is the simple or basic form. What we want to then do is pop pi on 4 into where cos of x is. And if you remember back to year 11, when we have our angles in terms of pi, we're in a radian. So if I want to pop that into degrees, because it's nicer to work in degrees, we're multiplying. And I think I've got it over to the side over here. I'll pop it in if it's not there. Okay, when we go, and I think I did this last lesson, radians to degrees, we're going to multiply by 180 on pi. And degrees to radians, it's the other way. We're going to multiply by pi on 180. So all I did was multiply my pi on 4 by 180 on pi. My pi's cancel out. I've got 180 on 4, which works out to be 45 degrees. So that's where the 45 degrees comes from. Now, back again to year 11 work. If you remember our special trig triangles, anything that has a 45, a 30, or a 60 in it is going to come through as an exact value. So if you look over here, we ended up with sine 45 and cos 45. So thinking of your SOHCAHTOA, pop that in there if you forget. So this is all assumed knowledge from year 11. Our sine is at opposite on hypotenuse, so 1 on root 2, and our cos is adjacent on hypotenuse, so also 1 on root 2. So what we end up here, our cos of 45 is 1 on root 2 minus our sine of 45, which is also 1 on root 2, which is equal to 0. So a nice, simple, straightforward question. Let's have a look at the next one. Okay, if y is equal to x minus tan x, we're going to integrate each part. We're not integrating, we're differentiating. We're going to differentiate each part separately. So when we differentiate our x, we end up with 1. When we differentiate our tan of x, and it's actually minus tan of x, our minus is going to stay there, and our tan of x turns into sec squared x. I'm going to pop in pi on 4 into that, but what sec squared x actually means, sorry, I just got interrupted there. So what sec squared x actually means is it's sec of x all squared. Okay, so we need to remember that. So when I'm popping in a value for x, I'm popping my pi on 4 in, what I've got is sec of pi on 4, and it's all squared. Now, sec on your HSC formula sheet, or you might remember, is 1 over cos. So what I actually end up with for this question is 1 minus 1 over cos pi on 4, and the whole lot there is squared. Pi on 4, do you remember what that was? Pi on 4, special triangles. We had cos of 45 degrees, going back to those, which is 1 over root 2. So what I then have is 1 minus 1 over root 2 all squared. The bottom is flipped upside down. We find the reciprocal multiplied by the 1, and we square it. So we're actually going to get 1 minus 2, which is minus 1 for that question. Okay, let's have a look at the second example here, and it says to use the chain rule to differentiate, but what we're basically doing is differentiating as we normally would. We haven't really referred to this as the chain rule, but what we're doing is finding the derivative of the function that is embedded in there in the cos function, and that would be 3. So the 3 goes out the front. Our formula sheet tells us that when we differentiate cos, we get minus sine. So we've popped our 3 out the front there, and we get minus sine, and that function from up there goes back into there. And that's the answer for that one. That's a nice simple one. Likewise, we do the same sort of thing with our differentiation of the tan function. Let's move that back over there. We've got y is tan 5x minus 1. When I want to differentiate that, I differentiate the function that's in there embedded with tan, and that would become 5. The tan differentiates to sec squared, and that same function, the 5x minus 1, goes in there. And that's the answer to that. Okay, tan of 3x over 2. Differentiating 3x over 2, we get 3 over 2, so that comes out the front. Differentiating the tan itself is becoming sec squared, and the 3x over 2 stays in there as well. So they're fairly simple, those ones. Let's differentiate these ones. So you really need to just think about what's happening in the next page. So turn over your next page and find y equals tan squared x. Remembering what I said a few minutes ago, that tan squared x is tan x all squared. Okay, so I'm going to think back to how we did this before. I'm not going to use substitution when I differentiate this. How I'm going to do this is the way we did it before when we had a function with a power and we were in brackets. We brought that 2 down to the front, and that's popped down here. We take 1 off that power, and that 2 becomes 1. The tan x would stay in there. And then what we do is we multiply by the derivative of what's inside the bracket. So the derivative of tan x is sec squared x. Okay, so our solution is 2 tan x sec squared x. Our next one, tan of x squared minus pi over 2. So we're differentiating. There's no power in here involved or anything like that. So it's similar to what we just did up above. Let's find the derivative of x squared minus pi over 2, which will become 2x. The 2x goes out the front. The tan becomes sec squared, and our x squared minus pi over 2 is popped straight back in there. Okay, now the bottom two are using the product and the quotient rule. And like we've been doing all along, we're looking to see where our x's occur. So we've got an x here, we've got an x here. We can't join them in any way. X is happening in 2 different functions, and the functions are multiplied together, so we're looking at the product rule. I'm going to let u equal e to the x. I'm going to let v equal cos of x. When I differentiate e to the x, I get e to the x. When I differentiate cos of x, I get minus sine x. So my product rule, which you're going to copy off the formula sheet, is written here. So my y dash becomes v du dx, which is e to the x cos x, plus u times v to the u dv dx. When I multiply my u and my dv dx, I end up with a minus sign, and that plus then turns into a minus. So I get minus e to the x sine x. I factored out an e to the x and got cos x minus sine x. So we're pretty good at that product rule now. The quotient rule, I think we're even getting better at. In this case, we've got cos of 2x on 5x. Please don't cross the cos's out or cross the x's out. We can't do that. Cos of 2x is independent of cos of 5x, okay? If they were both cos of 2x or both cos of 5x, that would be different. But in this case, there's 2 different functions with 2 different things in there. They're different. They need to be treated that way. So we have a quotient rule. My u is cos of 2x and my v is cos of 5x. They're written here. When I differentiate each of those, when I differentiate cos of 2x, I get minus 2 sine of 2x because I'm differentiating the function attached to cos first. That's 2. It comes out the front, and my cos becomes minus sine. Likewise, when I differentiate cos of 5x, the 5 comes out the front, and I get minus sine 5x. Okay, again, I want you to copy your quotient rule from your formula sheet, okay? So you're getting it substituted in the right way. It starts with v, it doesn't start with u. V du dx minus u dv dx on v squared. So I've got v du dx, which gives me minus 2 sine 2x cos 5x, minus u dv dx, that minus and that minus gives me a plus. So I get 5 cos 2x sine 5x. These guys can be flipped the other way, so it could be 5 sine 5x cos 2x. That's okay. And the bottom is v squared, so it's cos 5x all squared. You could put the little squared with the cos as well. At this point, I can't factorise that any further, so that is our answer.